For today's notes, we're going to go ahead and start by looking at a couple of the kinematics equations that we've been using in class. Something that I realized over the course of the last week and a half or so is that students are trying to just kind of copy and do what they're being shown with the kinematics equations, but maybe there's not really a clear understanding as to what they actually mean. So for the next few lessons, we'll start off by looking at a couple or one of the kinematics equations and just breaking it down and figuring out, well, what is each piece telling me of that equation? We're going to go ahead and start with these two because these are ones that we're going to be using more and more often inside of for the rest of the semester in our class. So both of these equations help us find the final position of an object based on various pieces of information. So how much time was the object moving? What was the acceleration of the object? Did the object have a starting position? And if so, what was the initial velocity, or in the equation on the right, what was the final velocity of that object while it was traveling? So I think the big thing that we need to realize is that these two equations are basically asking, what is my final position? And that's applied to both of these. So let's start to break down, what does each piece of this equation mean? For instance, the first part of this is pretty basic. In order for me to know where my final position is, I need to start with my starting location. So where was my starting location? And that can be said for both of these equations. So in order for you to know where you are ending, you need to know where you started. And this goes way back to when we talked about what does displacement actually mean. So we need to know, where did we start, where are we going to end? If we look at the second part of each of these equations, then what this is asking is basically, so you'll see that velocity is being multiplied with time. So ignore the fact that it's an initial velocity or a final velocity. Basically, it's just velocity multiplied with time. And if you're at all familiar with the fact that velocity equals distance over time, or displacement over time, then the fact is, when we multiply these two things together, we're getting a distance. And so what this piece of the equation is telling us is what distance has been traveled at that velocity over a period of time. And this has nothing to do with acceleration. So this is just looking at, what if you weren't accelerating at all? What if you were just moving along at that constant speed? Where would you end up? And that's the same for both of these. So distance traveled at that speed and time without acceleration. So the first part of the equation is talking about, where did I start? The second or middle piece of these two equations are basically saying, without acceleration, where would I end up? How far would I travel based on that speed and the time at which I traveled? Now for this last piece of the equation, with the 1/2 at squared, this is the part of our quadratic equation that is really bringing in, well, what effect does acceleration have on this object? So seeing that I do have acceleration, how far is that acceleration going to take me? What effect does it have on the distance I traveled in the previous part? So this part of the equation is basically asking, what is the effect of acceleration and what is it having over a period of time? So what's the effect of acceleration having over a period of time on the velocity and the distance that I traveled? So looking at these equations, we have these three parts. The first part is saying, okay, where did you start? The middle piece is saying, okay, without acceleration, just at that speed, how far would you have gone in that amount of time? The last part of the equation is saying, okay, what effect is acceleration having on the distance that I traveled? So if I'm speeding up at a specific acceleration, or if I'm slowing down at a specific acceleration, what effect is that having on the distance that's been traveled? And then what is it doing to that velocity as well? So let's see. And that's based on the acceleration that we started with. So let's go ahead and erase those and let's take a look at how the units work out. So since both of these equations are the same, then I'm just going to leave one of these up with the descriptors and we'll look at how the units work out for the other equation. So where am I starting? Well, that's measured in meters. When I take my velocity and multiply it with a time, then we're going to notice that my seconds are going to cancel out. We'll have seconds on top, seconds on the bottom, and we're left then with just meters. If we look at the third part, oh, and let me add this. So this is the final velocity multiplied with the time, all right? So we know where that's coming from. If we look at the last part, then we're basically just multiplying acceleration, which is meters per second squared, multiplying with time squared, which is basically seconds squared. And again, the seconds cancel out and we're left with just meters. And that's when we're multiplying acceleration multiplied with time squared. So as you guys can see, basically what we have is meters plus meters minus meters when all is said and done. In the left equation, everything works out the same and we're left with meters plus meters plus meters equals our final position. So I guess the point of what I'm trying to make is that these equations, when they're broken down, help us figure out not only where we ended, but we know little pieces about what's going on with the object as well. So where did the object start? How far did the object go just based on the time and the speed? And then what effect is that acceleration having on the distance that's been traveled depending on how much time it's been accelerating? So what we might do is take some time in class to break apart these equations and look at each individual piece and what it's telling us. As far as new material, let's go ahead and move on to the last few weeks of school and what we're really going to be talking about. And that's kind of the culmination of all of this, which is projectile motion in 2 dimensions. So the fact is, we've been looking at a lot of problems in which objects have either been going straight horizontally or straight vertically. And the fact is, not everything in life is governed by those two things. We have a lot of objects that are launched at an angle. We have a lot of things that happen at angles. So that takes understanding what's going on in 2 dimensions. We're going to delve into that today. We're going to look at this left problem this week. So examples of what if I'm standing somewhere and I launch something off of like a height, you know? So I'm basically already at apogee and I'm just launching from there. So if you take a look at this projectile is being launched with an initial horizontal velocity and it's in an elevated position. We'll examine this second problem later on, but not probably this week. Alright, so let's delve into what's going on with this problem. So here is a cannon that's being launched, or a cannonball that's being launched off of a cliff. Now, there are 2 things happening with this problem. Number one, the cannonball is moving horizontally. The second thing that's happening is the cannonball is moving vertically as well. So there's 2 things going on. The cannonball is moving out and the cannonball is going to move down. So let's take a look at what's going to happen horizontally first. So as the cannonball is shot, if we just look at what happens horizontally, what we're going to see is that that cannonball is just going to keep doing what it's doing. The only reason a cannonball is going to come down in this situation is because of gravity. But if we just look at the horizontal component, then gravity has nothing to do with that because gravity doesn't work horizontally. So the idea to keep in mind here is that what is this projectile going to do without gravity? So imagine if we launch this in space. So there's no gravity or gravitational pull in space. What is that cannonball going to do? Well, if there's no acceleration of gravity, then that cannonball is going to have an initial velocity and it's going to have a final velocity. And just like if we launched it in space, the initial velocity is going to equal the final velocity, and the final velocity is going to equal the initial velocity. In other words, the cannonball, without acceleration, is just going to keep doing what it's doing. It's going to travel on and on and on at the same speed forever and ever and ever, because acceleration of gravity doesn't work horizontally. Now, there is air resistance, but we're going to ignore the fact that there's air resistance for right now, because that force of drag would eventually slow it down. But let's just ignore that and just say, what is it going to do, for instance, in space? What if there wasn't any air resistance? It's just going to keep going and going and going like it normally does. All right, so that's what's going on horizontally. Let's examine what's happening vertically. All right, so ignoring the horizontal component, what is that cannonball doing vertically? Well, it's dropping. So that cannonball is, if we had just let it go and didn't launch it out of the cannon, it would have just dropped straight down. And why would it have done that? Well, because it started off with an initial velocity of 0 downwards, and then acceleration of gravity is taking over and it's starting to speed it up, and eventually it's going to hit the ground at some final velocity. So there's two things going on with this, which is why we look at these problems as being two-dimensional. We have basically the object traveling horizontally, it's just being shot out of the cannon straight, and then we have the vertical effects on that cannonball with gravity. So let's combine those two and take a look at what's happening with them now. And actually, something to keep in mind is that gravity accelerates objects downward, but it's unable to affect the horizontal motion of a projectile. So before we move on, that's like the biggest piece to this, is that gravity is pulling an object down, but it's not having an effect on the object horizontally, because gravity doesn't work horizontally. Alright, so let's combine these two pieces. First we got the horizontal motion, then we have the vertical motion. And the motion of this projectile is going to be a combination of those two things. So you'll notice that we can put this together in sort of like an XY plot. What is happening to this cannonball every second? Well, in the first second, it moves a little bit downwards and out. In the second, it moves a little bit further downwards and out. In the third second, it moves a little bit further downwards and out. In the fourth second, same thing, and then in the fifth second, we see that it actually is going to hit the ground, but it has also moved out. So we get to a point that it can't move anymore vertically, and that's going to stop its horizontal motion as well. So basically, the time that it takes to fall to the ground, that governs how far out that cannonball is going to reach. So now we can track the position of this object, and that's what it looks like. So this week is going to be totally about the fact that we're going to be looking at objects, and actually for the rest of the semester, we're going to be looking at these projectile motion objects. And the fact is that these objects are governed by the fact that they have horizontal and vertical motion happening at the same time. Every second that goes by, that cannonball is dropping vertically. But it is also traveling out horizontally, and it's the combination of those two things that's going to have an effect on what's going on with our projectile. So, combination of traveling horizontally, that's what we're going to be looking at. That means there's no acceleration affecting it, and there's also the falling of the projectile vertically, and that's when acceleration has its impact. All right, we'll discuss this more tomorrow and for the rest of the week.